Hi, my name is Paul Yip. I'm a product manager at IBM for Big Insights. And today I'm going to talk about Hadoop file systems, with particular attention to HDFS in comparison to spectrum scale. When people ask me, what is Hadoop, in the simplest terms, I tell them, Hadoop is just a really big file system and you can do stuff on it. And the way that this is achieved is by combining a bunch of nodes together, a bunch of servers together, to act as a single system. And in this way, we can actually achieve greater scalability and store lots and lots of data. So for example, file 1 here is broken into chunks A, B, C, and D, and those chunks are then spread across the cluster. The magic trick that HDFS does then is that even though those files are spread physically across multiple nodes, from a user and application perspective, it's still one logical file. And this metadata, which tracks where the blocks are actually placed, is kept in a master node called the name node. And so that name node is our map to all this data. The other thing that it will do is actually make multiple copies of these blocks and spread them across the cluster. So if we lose one node, at least we have 2 more copies from which to rebuild and reestablish that 3 times replication. Now, while lots of people are familiar with HDFS, most people don't know that there's actually a distinct difference between the Hadoop distributed file system and HDFS itself. Hadoop was always designed to be extensible. The way that this is done is by defining the Hadoop file system API or abstract class, and anyone who implements this API can be considered a Hadoop compatible file system. And as you would expect, a lot of people have taken the opportunity to do exactly that. Here's a list of many different file systems that have implemented the Hadoop file system API. A lot of these file systems were born out of necessity to address special use cases, special performance requirements, or maybe to address shortcomings in HDFS. And so in this way, GPFS, or spectrum scale, is no different. This picture is a good illustration of how HDFS architecturally differs from GPFS. What a lot of people don't know when they first start out is that HDFS is actually a Java virtual file system that sits on top of another file system. And in the case of Linux, very commonly this is ext4. And so HDFS doesn't really have a direct awareness of the underlying disks. And applications interact with HDFS through the file system API. On the right, you see spectrum scale, otherwise known as GPFS. And it's different because GPFS actually is intimately aware of the disks. It is a kernel level file system that's actually POSIX compliant. Now, spectrum scale has also gone and implemented the Hadoop file system API through this connector layer called the GPFS Hadoop connector. And so again, applications written for Hadoop interact with the file system API and get serviced by GPFS. But something really exciting happened late 2015. We introduced something called HDFS transparency. What this means is that the GPFS Hadoop connector can actually talk to applications like a name node. If an application talks to GPFS using HDFS protocols, GPFS will respond in kind, just like a name node. Okay, well, you might say HDFS is free and it's open source. Why should I care? Well, the first reason that a lot of people like is the fact that spectrum scale is a POSIX compliant file system in its kernel level, and it directly works with the disks. It doesn't sit on top of another file system. So first, let's talk about how to get data into Hadoop. Because HDFS is a file system that sits on top of another file system, before you can do anything with Hadoop, you have to actually do a copy operation from your local file system to the distributed file system. But with GPFS or spectrum scale, all you have to do is copy or move a file your traditional way into a file path that Hadoop can see. In fact, if you have applications that are producing data, they can produce the data on a path that Hadoop can see, and there's no movement of data at all. HDFS also doesn't really have a concept of a current working directory. So every time you work with a file, you have to specify the fully qualified path. With GPFS, again, because it's POSIX, I can move files using relative paths. Now let's say that I got 2 files that are very similar, but I'd like to figure out what's different between them. In HDFS, you'll often have to find creative ways to do things that you often take for granted. With GPFS, you would use your regular Unix approaches to compare 2 files. Now, because the distributed file system that spectrum scale provides is directly mounted and is local and is POSIX, you also save a lot of hops when trying to get data into Hadoop and getting data out. Often, we want to provide data to Hadoop to run our distributed analytics, and then those results need to get pushed out to other systems. So here's what a common process would look like for HDFS. On the left, we have systems that produce data, that's our raw data. We would write it to an ext4 file system. Then we do that copy from local to move it from the local file system to the distributed file system. Then we can run our Hadoop jobs. When we've got our results, to make these results available to a downstream application, we're going to have to copy that back out to that local file system, an edge node typically, and from there they can be ingested by these other applications. So in addition to the 3 copies of the data that I have within HDFS, I may potentially have extra copies of data just on the edges of Hadoop as well, because I have to keep landing it and uploading it. With GPFS, because the file system is local and it's POSIX, applications can see the file system natively. They can directly write and produce data just to a path that Hadoop can see. From there, Hadoop can run its analytics and leave it exactly where it sits. Applications that need to consume the analytics can directly mount the file system and actually read right off Hadoop. And here's even more benefits for POSIX. Existing operational processes extend naturally to Hadoop. Think about things like, how do I back up the tape directly? Can I do incremental backups? Because this is big data. Do I really want to back up everything all the time? How do I retrieve from tape directly to Hadoop? File system vulnerability scanning. This is really important for security. For compliance, sometimes we have to prove that a file hasn't changed. So Spectrum Scale offers something called immutable file sets. And finally, a lot of people are surprised when they learn that HDFS isn't really good at things like updates. Spectrum Scale is really good at updates and deletes, as you would expect a mature enterprise file system would. Now let's talk about disaster recovery. Because while every distribution will say they can do replication over large distances, it's really important to understand how this objective is achieved with HDFS versus something like Spectrum Scale. A key technology we need to understand is something called distributed copy, or DistCP for short. This is an open source tool for copying files at scale. And the way it does it is through MapReduce. It's basically just like any other MapReduce application, and it reads files from one cluster and writes it to another using a parallelized method. But this tool was never really designed to be a replication technology. And let me just take a moment to quote something that is right off the distributed copy apache.org website. It says, "Distributed copy's MapReduce pedigree has endowed it with some quirks in both the semantics and execution. After a copy, a user should generate cross-checks to verify that the copy was truly successful." So what this means is that any technology that builds on top of distributed copy needs to also do some checks and balances to make sure that the copy was successful and complete. So the point I'm leading to here is that the approach to disaster recovery really matters. On the left, the HDFS approach is to use tools that use distributed copy underneath. And there's different names for these tools, but generally they're wrappers for distributed copy that help with that reconciliation of data. The granularity of the replication is file-based, and it's also a user-scheduled job. And because it's a MapReduce application, it's actually going to allocate containers from Yarn that would otherwise be used for real work. The GPFS approach is really different. Because Spectrum Scale is a kernel-level file system, we can use kernel-level metadata to support replication. The replication is not file level, it's actually block level. So if we're always appending to files, for example, we're not re-replicating those files, we only need to replicate the differences in the blocks. Instead of being a user-scheduled job, this is a system-level service. It's resilient and self-restarting. The wide area network, or WAN, is assumed to be unreliable. Finally, instead of being a Java-based MapReduce application that runs as a user job, GPFS replication runs as a system-level service that is resilient and uses minimal memory and CPU. Now, often when customers set up a DR cluster, that secondary site is not really active. And that's really wasteful if we're talking about very large clusters. Instead, it might be a better approach to take advantage of Spectrum Scale's replication to run active clusters, where workloads are distributed geographically, and one site can fail over to another site if there's a failure. Now at this point you might be thinking, wow, that's really cool stuff, but you had me at POSIX. Let me tell you what else Spectrum Scale can do. A lot of people standing up Hadoop for the first time think of their world like this. Now whether you choose Spectrum Scale FPO or HDFS, data resiliency is handled the same way. We're going to make 3 copies of the data and spread those chunks across the cluster. However, as the data gets older, it will become inevitable that a lot of this data will lose its value or will no longer be accessed. and that 3 times replication cost can really start to add up. With Spectrum Scale, you can actually attach network attached storage, so you can define a policy that says if a file has been opened in 6 months or a year, that it should be automatically moved from direct attached disk, where we have 3 copies, to the network attached disk, which only has 1 copy of that file. And so now you're saving a lot of trees, saving lots of money, and also containing the growth of your cluster. On top of that, you can define policies to automatically destroy the data as well, and this will free up space automatically. Now, even though that data has moved from one part of the cluster to another part, the data remains available to Hadoop. The file path hasn't changed. So extending my prior example, if data has been accessed in more than, say, 2 or 3 years, we can actually say, move those blocks to tape, but keep the files online. Make them visible to the file system. But if someone accesses those files, we can still get to them by dynamically retrieving them off tape. So again, the best part of this is to an application or to a user, this still all looks as one file system. So let's just recap what you saw. Spectrum Scale extends Hadoop file systems in the way that it was designed to be extended. It is POSIX compliant, and so it makes enterprise integration easier. Think about those backup scenarios, incremental backup, moving files, copy files, writing files. Spectrum Scale goes further by actually speaking HDFS like a name node, so that your applications will code to it as if it's HDFS. If you're concerned about disaster recovery, Spectrum Scale has the most efficient way to do this and can support active-active clusters. And finally, Spectrum Scale provides information lifecycle governance capabilities not found anywhere else. Thank you.